After a short break due to busy schedule, so I'm back. In today's quick video, we will dive into how to predict sand production in oil field using geomechanics. Of course, if you find this video useful by the end, of course, don't forget to subscribe and share it with your friends, colleagues, or within your network. Before starting and going through details, that's a little about me, that just along with a brief introduction for those who are not familiar with my profile and technical and scientific skills. The question is, what is sand production in oil and gas reservoirs? So as you know, the sand production occurs when sand grains or rock particles come from the reservoir as produced along with oil or gas, or also even with water, due to some mechanical failure of the formation. So this is like the production of unwanted sand within reservoirs, which during the reservoir come unconsolidated or weak reservoirs. So the reservoirs, when it will become unconsolidated or weak, it will cause the grain to flow with oil, gas during the production, the normal production. But the question is, why do this grain or do these sand grains or rock particles get produced unwanted production along with oil or gas? The answer is that the sand production occurs when the stresses in the reservoir or even though around the wellbore exceed some criterion, which is the rock mechanical strengths. It will cause the formation to fail and the sand to flow within the wellbore. So it means that the sand production in reservoirs is directly linked to stress changes caused by the reservoir depletions. So when we say production, automatically in our head come the depletion. So under initial conditions, we have the effective stress equilibrium, where the effective stress equal to total stress minus pore stress. So this is the balance, and under this balance, the rock remains stable. When the production starts, so the reservoir pore pressure here, these in the right picture, those soldat or those army of the reservoir, which are the pore pressure. So the reservoir pore pressure decrease due to natural depletion, means that due to natural production or the natural flow from the reservoirs. While the total overburden stress remain nearly, you can say, constant. So this change cause an increase in the effective stress, which will increase the overburden stress above the reservoir. So we say that effective stress equal total stress minus pore pressure. As the effective stress increase, the rock framework is subjected to high loads. Means here we have a high load from the overburden of the reservoirs. So in the weakly cemented or unconsolidated reservoirs, this phenomenon or this stress increase leads to grain rearrangements, so which leads also by itself to microfracturing and losing of this cementation, which will progressively weakens the rock. As a result, even though the cohesion and the frictional angle will decrease, and in some cases, so this will lead to reservoir will be close to the failure envelope. So the sand production occur when this stress state around the wellbore or even the perforation reaches the failure envelope or the failure limit within the Mohr circle criterion. So the Mohr circle criterion links the shear stress and the normal or principal stresses. I will explain. So when you see here the circles, so we have the initial state, which is when we have the initial before production initial state between effective stress, total stress, and pore pressure. When this pore pressure decrease, we will have like shifting. We will shift in our envelope and we will increase the effective stress. So if this effective stress increase, if it will exceed the failure envelope, we will have sand production, which is equivalent to weak reservoirs. Okay. Now, So we will just brief explanation. So the sand production, just as a recap, develop after the reservoir has been in production for some time. So if the reservoir is still no production, so you are safe in terms of sand production. After the depletion or after the production occur, you will have the change in terms of stress equilibrium. But since you are in Wellbore, so your stress, we will talk about the hoop stress. So we will have an increase in hoop stress around the perforation and also even around the Wellbore. Another point to explain is even if, for example, in your initial plane or initial production, you have some geological data and it shows that your reservoir is consolidated reservoir, but so means that it is sand free. But there may in some point come where your perforation or your wellbore fail and you will fall under sand production area. So the sand production is a result of or from stress redistribution or stress disequilibrium between this effective stress and total stress and pore pressure, induced of course by reservoir depletion and wellbore drawdown. When you see here this at right of our slide, we see that we have some schematic explanation about the relationship between drawdown or production, or to be more precise, between depletion and sand production. But the question that everyone can ask, what is the link between so because we are not all geomechanics engineer and we are not all geoscientists, we have not all the geological background, so we will try to explain. Because as you know, when you work in a subsurface environment, you have the geophysicist, geologist engineer, you have the reservoir engineer, petroleum engineer, of course, and the production engineer in some cases. All of these guys has his own background and his own vocabulary system. So sometimes the geomechanical engineer and the petroleum engineer don't talk the same languages, because the petroleum engineers think about flow, think about making the reservoir flowing. The reservoir engineers also sometimes think about the simulation, but the geomechanical or the geologist think about how the rock it will behave during production, pre-production and also post-production. So we will explain. At the initial condition, you have the initial drawdown, as you know, but it's not the conventional initial drawdown. We talk about pressure, reservoir pressure minus well pressure. But in geomechanics convention, we will use the reservoir well pressure minus reservoir pressure to avoid the minus sign within this equation. So first we start by making the reservoir flowing as initial drawdown, and after that we have in this point the final drawdown. What is the relationship between these two, both drawdowns? This is the limit between safe predicted solid free production window and failure or dangerous window of solid production. The relationship is based on what we call it the UCS, which is the confined compressive strength. So the criterion is simple. Do not go deep details. So to not have sand production, this equation should be verified. So the sigma theta, which is the hoop stress, should be superior or equal to UCS. And we have to build the shear criterion, we have, so this is the shear stress, which is the cohesion plus the normal stress multiplied by tangent of a friction angle. This is all the criterion that should be verified. Okay, so now we understand. And the hoop stress equal this equation minus delta P, which is drawdown. Okay, if we understand this, so now you can ask the question how we can move forward and having our simulation. Initially, we have a drawdown, but after that production continue to flow after depletion. Logically, the reservoir pressure will decrease. And I know that you will ask me question how you can talk about decreasing drawdown, and since we are producing, so we should increase. So the production engineer think that he should increase the drawdown to have more flow, but this is logic. But in our simulation or in geomechanics point of view, you should be careful. So based on this simulation, you have this limit to not exceed. So if you exceed this limit, you will fall in the red window. Based on this simulation, you will not avoid sand production, but you will predict when you will have sand production. So this simulation will help you to have reservoir management, means that you will use some cost reduction. So rather than going flowing your reservoir and producing until you will have a failure, not expected or unwanted sand production, based on the geomechanic or this result simulation, you will all subsurface team can have an idea about when the sand production occur. So this not means that we have to reduce the drawdown to have a good production. But now, this is when you arrive to a critical point, this is your final drawdown. And if you exceed this final drawdown, you will have sand production. But during all this time, you have a lot of remedial plan, and you have to balance between your production, closing some wells, making some remedial plans, decreasing production from some wells, because you are not producing from only one well, you are producing from a reservoir. So you have to balance your drawdown based on your production from all the wells, not only from one well. What you see here is final drawdown from the reservoirs. So from the reservoir. So you have to make a balance between well and reservoir and geomechanics and all the simulation. Not let only the production and the engineer to decide about the drawdown, or only the petroleum engineer, or only the reservoir or geologist or geomechanics engineer. This is teamwork. So everyone should give his inputs to have a safe production or to manage the reservoir. If everybody, I think that I give explanation. So the question is where we can have the UCS. So the UCS, you can get it from the laboratory test data, or even though you can have it from some empirical equations. So what you should put in your mind that you don't try to do not exceeding this threshold between stable and unstable or failure solid production. I think that we can go quickly to calculate critical drawdown in a reservoir using geomechanical parameters listed below. For example, if we have a depth of 20,000 meters, SH max 35, SH mean 25, with a pore pressure of 20 of megapascal, of course, and UCS 15, cohesion 5, and friction angle. The question, I give you just a few seconds to define the theta. So what is theta? Theta is the critical drawdown is evaluated under theta equal 90 degree, where tangential stress around the wellbore is maximized. So the sand production initiate when this drawdown induced, and the effective hoop stress exceed what we talk about the Mohr Coulomb failure criterion, defined by the UCS, of course, and the friction angle. So the result quickly are, if we apply all these numbers, you can verify by yourselves. It will give us 20 minus PW, which is the wellbore pressure. This is the condition. So the delta P equal 15 megapascal. Normally the rock fails at the UCS 15, so at this condition, and we can deduce the wellbore pressure that will not be exceed. So you will place your final drawdown, which is 15 megapascal. You draw your limits, and based on this number you can manage your reservoir. So before starting the production, you know that if you will attend this drawdown, but yes, to be careful, this drawdown at this reservoir pressure. Okay, so this is based on reservoir pressure, because the reservoir pressure depends on the production. So when you produce a lot, or what if the reservoir, your reservoir become quickly unconsolidated, so it means that you will drop in the pore pressure and you will arrive to this point. So this is your final critical point. You draw this point, this line, and you have your safe limit of sand production. Just quickly, what are the remedial plan for sand production in oil and gas reservoir? We will not go deeply in those solutions, but just for examples that we have the frac pack, which is like short hydraulic frac pack, and we have also the gravel pack, which will disable the sand production from the perforation. I think that we arrive to the last slide. I can say thank you very much. Shukran lakum. Gracias. Terima kasih. Merci beaucoup pour votre attention and see you in the next short video.